Hi guys, so my name is Robert Frazee. I was the group reporter for Group 1's refrigeration cycle experiment. It's a week late, sorry I was out of town, so here we go. Brief overview of the refrigeration cycle. It's basically the Rankine cycle in reverse. We start off by compressing our fluid, in our case it was R134A. After that we go ahead and run it through a condenser. That is where we reject heat, in our case, or for the experiment that we ran, that was into a water reservoir. We then pass it through a expansion valve, and then finally through an evaporator, which is where I actually absorb heat. Again, for the experiment that we ran, that was from a water reservoir. One thing that we're going to talk about is the coefficient of performance. This is basically equal to the amount of heat that you moved for the amount of work that you put in. So for example, if you have a coefficient of performance of 2, you're moving 2 units of heat for every unit of work that you put in. So for our first exercise, we recorded a couple of values, including the compressor power and the conditions through the condenser. Using that, we're easily able to find the power and the heat that we rejected out into the cooling reservoir. We can calculate the coefficient of performance by simply dividing those. However, that does not account for the heat added by the pump. We can simply subtract 1. However, it's important to note that this is an approximation, as we did not actually record any data for how much energy that we were absorbing from the evaporator, and as we'll see later, that kind of gets important. So, in terms of trends, as we change flow rate, the lines with these 2 lines are plotted over here. The triangles are plotted on the right. Sorry, I didn't make that more clear. There's not really a clear trend in any of these, with the exception of the compressor inlet temperature, which did increase as flow rate increased. However, since we ran these in reverse order, there's a possibility that that may have been temperature or time dependent. So for exercise 2, we adjusted the condenser flow rate to 6 liters per minute, and we collected these parameters. Of particular note is this expansion valve outlet temperature, as that is significantly superheated at 3 bar. We were able to then, using some pretty standard interpolation, find the state points for the compressor inlet, outlet, and the condenser discharge. Going by the packet, we were to assume that the enthalpy going out of the expansion valve was equal to coming out of the condenser. Exercise 2, more of the same data. Those temperatures are really the only things that changed. The pressures remained fairly constant. And again, we're able to calculate some additional state points. And one more time for good measure, this time at 3 liters a minute. Again, pressures remained constant, temperatures did change. Now, some stuff about that state 4. The temperature data that we got doesn't match with what we would have expected from an ideal process. If we assume that that expansion valve is outputting at 3 bar, that's actually significantly superheated, which means that there's no evaporation in the evaporator, which means that we're not actually removing heat. Now, there are a couple of ways that that can be accounted for. First off, there is likely a pressure drop across the evaporator. If we assume that the expansion valve is putting out some kind of vapor-liquid mixture, that would be around 4.5 bar, which is not unreasonable. And if we assume that that would actually allow evaporation to take place in the evaporator, which is important for a refrigeration cycle. Additionally, the inlet to the compressor is superheated instead of perfectly quality 1, and the outlet of the condenser is slightly subcooled. So we're able to get a couple of options for our pH diagram. Colors aren't quite working out, but these 2 lines are brown. That's what we would have expected. The blue line is closer to an ideal process, with this red line representing the possibility of expanding to 4.5 bar, evaporating from there, and then dropping across the evaporator. So I did not put the numbers up here because they didn't make sense, but I tried to calculate the coefficient of performances for the 3 varying flow rates, and the numbers that we got were in the neighborhood of 5.5 to 6.5, which is significantly higher than we would have expected, especially compared to the numbers that we got from our first exercise. A couple of ways that the numbers I was working with didn't quite match, so there is going to be a pressure drop of some kind across the evaporator, probably not 1.5 bar. Also, when we performed the experiment, we did note that the system was reacting very sluggishly. We would change the flow rate and it would take 10 to 12 minutes to not even reach a steady state condition. I'll also note that when we arrived at the experiment, the compressor was running with no water flowing through the evaporator or the condenser. What I believe happened is, since that was just left running, more and more heat was put into the refrigerant, and when we got there, experiment 1, we were actually measuring heat being rejected from that refrigerant rather than actual heat being moved in a cooling cycle. There are other possible sources of error. It's possible that we just read off the wrong measurement, although we did this 3 times and none of us caught it, so I don't think that's too likely. There's also a possibility that the sensor or expansion valve had some kind of malfunction, but that was outside of the scope of this experiment. So, any questions?
So do you think that performing this experiment and seeing the outcomes of it is going to affect your future in any job? Do you think it will have any impact on it?
Maybe. Definitely good to, what I would prefer to do and what I would have done in the real world is when we started seeing this data that didn't line up is go and run it again. Unfortunately, because of this lab, we didn't have time to do that. And there's probably something also to be learned. If it was the compressor just overheating the fluid, something to learn about automatic shutoffs.
Okay.
Any other questions? All right, that's all I have.